somewhere?
Yes, recording has started. Yes.
Okay, great. Okay, so I believe it's now time to start. So I would like to thank all attendees for this first webinar in 2024. This year theme will be focused on production logging. Okay, so the main year theme will be everything related to the tool, um, tool physics, manufacturer interpretation. The first webinar will be with the Schlumberger Advanced Production Logging System. We'll talk about the Ghost tool, okay, and sorry, the FSI tool, okay. Maybe you'll talk about Ghost sensor, optical sensor. Mostly will be presented by Mr. Syed Aamir Aziz. Ammar or Amr?
Amir.
Amr Aziz, okay, Mr. Amr Aziz. He's a senior production and integrity engineer with Schlumberger, I believe based in Dubai, UAE.
Oh, yes, I'm
There,
based in Abu Dhabi. Yes.
based in Abu Dhabi. Okay. We will have 10 confirmed webinar this year. We will have two with the Schlumberger this year, two with Kappa, one with scientific drilling, one with open field in coordination with the Allseer, and one from ISP, which is a Plato software a designer, and with TGT, and we'll close the year with TGT too. Okay, I'd like to thank all these companies for their time and effort to sponsor all these technical events. As the last year did, okay, for any learner, I just need to put it as 2024. Uh, any attendee will attend 6 live webinars. You will get a very special certificate. Last year, there was 2 attendees, Mr. Aus and Mr. Delvin, managed to get this super certificate for integrity. Okay, and just a reminder, we saw many people work in Iraq, or they are live in Iraq, but they register in different chapter. Okay, it will be really nice if they can change their chapter to Iraq. Okay, this is all from my side. Just in case this first time meet me, I'm Mazil Hilali. I'm the chairperson for SPWLA Iraq. I will leave the mic for Dr. Mohammed. He is the VP of Technology. Okay, Dr. Mohammed, the mic for you.
Yes, Mr. Mazen, can you hear me, please?
Yes, really clear.
Okay, okay. Thank you, Mr. Mazen. And hello, Mr. Syed Aamir Aziz, and all attendees in 2024. This is Muhammad Jawad Zainul Abidin, Vice President of Technology in SPWLA Iraq chapter. Also, I am a senior faculty member in the Department of Petroleum Engineering at the University of Kirkuk. Society of Petrophysicists and Well Log Analysts Iraq chapter would like to introduce to you free webinar regarding SLB Advanced Multi-Array Production Logging Tools by SLB Company. Tools theory along with case studies to be presented by Mr. Syed Aamir Aziz. We hope to spend a good time today with our first webinar into 2024. Thank you again and welcome to you again.
Thank you, Doctor. Okay,
Thank you.
and thank you. And the mic for you, Mr. Said. You can start your sharing.
Okay, thank you, Mazen. Thank you for the introduction. Good morning, good afternoon, and good evening, all. This is Syed Aamir Aziz. I'm a senior well integrity and production engineer, currently working in Schlumberger, Abu Dhabi. I have more than 15-year experience in fields of oil field for the production logging and well integrity log analysis and interpretation. So today I have got this opportunity to present. Let me share my screen and okay, you can see my screen, right? To the
Yes,
slide view.
clear.
Yeah, okay. Okay.
Crystal clear.
Okay, so today I'll be going through the FSI flow scan imager is a advanced production logging tool, especially designed for horizontal and highly deviated wells. So we'll have to follow this agenda. First of all, we'll be talking about the basic concept of production logging, why we run the production logs, what are the applications of the production loggings, benefits, advantages from the client perspective, and from the as a reservoir engineer or petrophysicist perspective, why do we need to run the production logging and what problems can be solved by production logging. Then we'll have some kind of PL production logging workflow as we usually follow for the acquisition and interpretation. Then I'll be describing the techniques of the production log interpretation uh, in vertical wells, which is simple, and then more complex in the horizontal well. And the tool used for the horizontal logging is FlowScan Imager or FSI. Will be having overview of FSI tool and how it work, what are the sensors, and then in the end, I'll be describing some examples or the case studies for the FSI. So let's start by the very basic question, what is production logging? So we know the production logging is basically the measurement of downhole fluid parameters or the downhole fluid measurements in an oil well or the gas well or is the producer or injector when we want to know the production at downhole condition and the zonal contribution from each perforation, what is being produced and where it is coming from. And for example, what are the source of water production, what are the source of gas production. So all these information are acquired by running production logging tools or PLTs in vertical or nowadays in the horizontal or highly deviated wells. So the basic concept is to know the production profile downhole. And this is the final answer of the production logging. What we get from the production logging is the production profile of water, oil, or gas. Usually, water is represented by blue color, gas with the red, and oil in the green. So from each perforations, let's say you have a set of perforation in vertical well. So what is being produced and where that fluid is coming from. So all these information and more than that, it's not only about the production profile, but we get the many other answers from the production logging that we will see in the next slides, that why we are running these production logging tools. So there are some basic questions. I mean, this is why do we need the production logging? Why a reservoir engineer decide to go for a production logging tool or PLTs? Why a petrophysicist or any other engineer is looking for what information is looking for? So there are some basic questions, or what and how much a well being produced, right? Where it is coming from, water, oil, and gas. So if we want to know any contribution, what is the well is producing, how much is being producing, usually we get the surface test results and we know from the test result without running the production logging tool that how much well is producing, but we don't know where that fluid is coming from. That's why we need the production logging tools to go downhole and locate the water, gas, or oil entry points to do some remedial work or to know the well profile or the production profile. In case of injections, so well could be either uh, injector or producer. So if it is an injector, we want to know where is the injection water or gas is going into which zones. Why the well is having high water cut. So in case well started cutting water, then definitely we want to stop that water and do a kind of bridge plug or any other remedial work. But first, by running production logging tool, we would know what is the source of that water. Is that a specific zone which is producing water, or any, it's a water flooding, or so without running the production log, we would not be able to know where exactly that water is coming from. Similarly, why a well is start having a high gas oil ratio. So could it be from the gas cap? Could it be from if the well started to produce below bubble point, then you might have a gas influx. So we need to know what is the source of gas in the well production, right? Is there any cross flow? When the well is in static condition, so we might have a downhole cross flow because of the two zones having a different pressure or differential pressure. So the high pressure zone will produce some fluid, and that will go eventually into the low pressure zones. That we call it cross flow. So it happened very common because of the pressure difference in the smart completion as well. We have seen many cases where we see the cross flow. Even in the barefoot open hole completions, we see a cross flow, and this is a very, very serious issue of the well. So we want to know if there is any cross flow, if we are losing fluid downhole. Secondly, we want to know, is there any leak? How is my completion integrity? If the completion what is installed, is it working fine? Is there any leak? Are we getting fluid from the unwanted fluid from any zones? Are we losing fluid from because of the integrity of the or the leaks, or maybe the completion apart, or is have anomaly? So whether we are gaining fluid, whether we are losing fluid because of these completion problems. Was the completion design was effective? So, these completions nowadays, inflow control devices or pre-perforated liners, and there are many kinds of completions, smart completion downhole. When we install these completion, definitely we would like to know the effectiveness of those completions, if those completion designs are really working or not, or they are restricting the water as they are designed or not. So production log, after the successful run of the completion, we need to run the production log in order to evaluate the effectiveness of that completions, right? Or ICDs or any other smart completion. Do the well need stimulation or any intervention? From the production logging results, we would know if any well need any intervention. If the well is being acidized, then we need to know the performance of the acidization, if that acids really makes any difference in terms of production or injection. So all these questions a petrophysicist or a reservoir engineer must ask before running or choosing the production logging tools. And by the way, all these questions is basically for the production management or well integrity. So this is one aspect of the production logging. Nevertheless, the other aspect of the production logging is the reservoir management. This is on a bigger picture. So we do a production logging on a well by well scale. Secondly, we use this production logging data as on a bigger picture, on a reservoir level or on a reservoir level scale for the reservoir management. So what are the uses of production logging data in terms of reservoir management? Is the reservoir dynamic model is updated? So this is mainly for the reservoir, and this is, let's say, long-term design or long-term benefits of the production logging. On the left-hand side is on the well basis, and the short terms when you have to decide something on the basis of well production or well management. On the right-hand side is for the reservoir, and it's a long-term. What is the current oil water contact or gas oil contact? Because reservoir condition keeps changing when the reservoir is put on when the fields are being developed and a lot of wells being drilled and put on production. Then the reservoir, oil water contact, gas water oil contact, these contacts usually they vary with the time. So we need to closely monitor as a reservoir engineer all these parameters of the reservoir and put into our reservoir model to get the updated dynamic reservoir model. What is more important is the pressure changes in the reservoir. So pressure, because of the continuous production, the pressure of the reservoir is keep changing. We need to monitor closely. Are we start producing below bubble point, which means your valve will, or the reservoir, if it is goes below bubble point, then you start having the gas, the liberated gas, which is from the oil, and that sometimes hinders the oil production as the gas has a high mobility. So it tends to flow more and it restricts the residual oil in many cases. So it's very important to know the pressure of the reservoir if we are below bubble point or above bubble point. Is there any changes in reservoir PVT? This is again very important. How effective is the water or gas flooding? So usually in many countries, many regions, oil fields are managed by the water or gas flooding in terms of they put the water injectors or the gas injector in the peripherals of the fields, and then they start producing from the middle of the field. So definitely as a reservoir engineer, we like to know how is the saturation or the water flooding is going into the reservoir. How is the sweep efficiency? Is there any water fingering? Is there any, high permeability streaks in the formation which brings water or early water breakthroughs or early gas breakthroughs? How does the injection change the reservoir saturation? So when you put injection strategy, then definitely you want to monitor the injection flood or water flooding because of the injectors and how effective it is working as a strategy to produce more water and restrict the produce more oil and restrict the water. So all these information can be obtained from the production logging, and hence the reservoir module can be updated and all these parameters. So what are the applications? Like we discussed already, we have a lot of different application of the production logging. It's not simply the to know what the well is being produced, but this knowledge of production logging or the data can be used in many aspects. So you can see here in the let me Okay, so here you see the production logging data is used for basically two purposes. First is the production management, and secondly on the reservoir management, which is on the right-hand side. So the production management is the reactive fast loop when you have to decide to run the production logging in terms of protection or restoration on generations, right? And there are many applications like to know the cross flow, zonal fluid, injection profiles, reservoir pressure changes, gas banking, PVT, all these, and also the well integrity issues like leaks, corrosion, scales, all these on the well bore basis. So this is one of all the applications of the production logging in terms of production management. On the other side, in terms of reservoir management, we use this production logging data for simulation, mapping and monitoring, like I said, gas oil contact, depletion, sweep efficiencies, skin factor, reservoir boundaries. So all these applications are for the production logging data, and we get the answer of all these questions by running the production logging tool. So these are the main application. Now, the technologies we use as a downhole tools for the production logging, we have the oil industry is being used since many years, many decades, all these production logging tools from simple to the complex, and then there have been a lot of advancement in the production logging tools. So to know the downhole flow, because we know one of the basic objective of the production logging is to know how much as the well is being produced or the flow profile. So the very basic tool for the production logging is a flow meter. we call spinner or flow meter, which is this one here, right? Then we have some fluid identification tool. So when we know how much is being fluid, but we want to know what is being produced, whether it's water, oil, or gas. So we need to distinguish different fluids, water from oil or gas from water. So we need some downhole measurements to know or to identify the different fluids. Similarly, we have a density tool, which we call it gradient-manometer, or there are nuclear fluid density. So this density is not to confuse with the formation density. This is the production fluid density. So let's say if a well is producing oil, mixture of oil and water, so this density will compute or will measure the density of the fluid. If it is 50% water, 50% oil, so that density will, based on the density, it will tell us how much is the percentage of the oil or percentage of water based on the downhole fluid density. But apart from the density, we have direct tools or direct measurements which can directly measure the water inside the wellbore, which we will show in the next slides from the electrical and optical probes. Similarly, we have inline spinner. This is a secondary or auxiliary spinner in case the main spinner stop turning because of any downhole condition. Then we have a backup or secondary spinner. We call it inline spinner. Then there are some usual basic sensors, which are temperature. Temperature is very important, by the way, in the production logging, and it gives a lot of information about the downhole condition, about the downhole flow, especially the leaks. So we have temperature and pressure, and we have a noise tool, HFND, also, which we call it for the noise and leak detection. So on the top side, you will see that these are the conveyance method of these production logging tools, whether we use the electric line or the wire line, slick line. We have a fiber optics. Then for the horizontal logging, we use normally tractor and coil tubing for the horizontal logging. To push the tool into the horizontal wellbore, we definitely, it's not by gravity by itself, so we need some either the tractor which push the tools, and these tractors can, even while going down, we can log the production logging, and we can pull by the normal cable. So we do different passes or the logging in the wellbore up and down. So we use these conveyances for carrying and giving the power and recording these production logging data. On the rightmost side, you see two simple tool strings. So the first one is normally is a very simple tool string used in the vertical wells. So we have a spinner on the bottom, right, which measure the flow rates. Then we have fluid identification sensors in the spinners, so on the arms of the spinners. So we use sensors called GHOST and DEFT. These are basically the probes or which identify or distinguish water from the hydrocarbon or gas from the water. Right, then we have inline spinners, density and normal basic sensors, temperature, pressure. So this is a simple tool string normally used in the production logging as a vertical for the vertical well. For the horizontal and highly deviated well, it's a different technology that we will show in later slides, that what tools are used, what are the array tools. So it's a two different approach, two totally different things when we talk about the vertical well and we talk about the horizontal well. In terms of production logging, it's a entirely two different approach. So basically, the production logging workflow starts with the pre-job. When engineer or petrophysicist is select a candidate well for the production logging, let's say for the zonal contribution or any of the objective, whatever is the objective of the production logging, like we discussed earlier. It could be many objectives. So once we identify that a well need to be logged with the production logging, then we do a pre-job planning, which involve to know the objective, what is the objective of the job. Then we gather the information the previous information or the basic information on the wellbore, like completion, how is the completion, is it a open hole completion, is it a ICD completion, or what type of completion is there, then we might need some open hole data. It's good to have, it's not mandatory, but it's good to have the open hole density, porosity, and some open hole data. But what is more important is the deviation survey. So normally we get this before running or in the job planning phase. We get the deviations because the deviation is affecting the downhole flow and downhole flow regimes. So it helps us in the interpretation of the production logging. How is the deviation, downhole deviation, right? So this after the pre-job, when we have all these information, then the second phase is the job execution on the well site, right? Normally, this involves a logging truck and production logging tools. If it is a vertical well, then we go with the normal wireline, which can run the production logging tool with the help of gravity only in the vertical, and the low deviated wells, let's say up to 60-degree, we can go with the wireline. But if the deviation is more than 60-degree or 70-degree, then we need either coil tubing or the tractor to push the tool to the bottom, and so that we can acquire the production logging data. So during the job execution phase, we do run the logs and do get the real time. So normally production logging tools, or the tools which I'm going to show in next slides, they are surface readouts, but still we can use those tools as a memory mode. We get the memory data inside the memory. When we pull out of the hole, then we download the data. But for the real-time decisions, it's very important to run in a real time with the surface reads route, so we can decide on a real-time basis if there is any QC, or we need to repeat the passes, or the data quality issues and all these. So it's very important to see the data real time before the rig down to decide if the data is enough, or it has a it's a good quality data which can be used for the next phase or interpretation. So this data is usually sent from the field to through the internet to the town, and we, as an interpretation engineer in the town, we do the data QC, and then after we are satisfied with the data quality, then we start our interpretation. And interpretation usually takes 24 to 48 hours, and the final answer product is on the picture. You can see that we gives in terms of downhole flow profile or the downhole production profile, from which the client or you will know that what and how much is being produced from each zones or each perforations, or from the downhole. So we get a complete downhole flow profile after the interpretation, and the answers in the tabular form, and and other interpretation comments as in form of full interpretation report. So that's the usual workflow we follow. Now, talking about the production log interpretation, like I said earlier, production log interpretation have a two basic approach. One is used for vertical well, which is totally different, and secondly, used for the horizontal well, which is more complex and different approach, and different even the different tools are used for the production logging. Why is that? Because the flow behavior inside the wellbore is totally different in the vertical wells. Let's assume a vertical well. When you have different sets of casing, you have a surface, intermediate, and production casing, and let's say the production casing is perforated in different zones, or you have barefoot open hole completion or whatever. So this is a basic design of the well. So when the well start producing, then we do this production logging during the dynamic condition when the well is being on the production. So usually, as a approach for the production logging, we do a static survey, and in the static condition, which means the well is shut in, and then we do for the production profiling, we do production logging while the well is flowing. So we need to flow the well for the production logging and keep it flow until it stabilized in terms of pressure and temperature. And when the well is having achieved the stable flow conditions, then we start logging across the zone of interest, normally in the production pipe or the production casing, across the perforations, or any zone of interest, or across the horizontal section in the horizontal wells. And in vertical well, where are the perforations or the flow zones, right? So we do multiple passes of production logging inside the across the perforations. And since the well is in the production, so let's suppose a scenario when the well is producing oil and water. So in vertical well, this oil and water will form a kind of mixture, right? So they will not flow as a separate phase, but they will form oil and water, or gas even. They form a homogeneous mixture and start flowing up in the well to the surface, right? So the production logging in the vertical well, we measure different parameters, like a flow meter measure the rate, and the density or the holdup measure the mixture density, or the holdup of the mixture. And then we can convert this into the production profile to know how much each phase is being produced. The second approach, which is more complex, is horizontal well. So nowadays, we know a lot of horizontal wells is being mostly drilled, some long horizontal wells, or a maximum reach, maximum reservoir contacts well, which can even go 30,000 feet as an horizontal lateral. Then we have in the Middle East, especially some multilateral wells being drilled, and different types of designing of the like fishbone wells. And so these horizontal wells are very complex in terms of flow behavior when they are put on the production. When we monitor the production logging, it's a totally different approach in terms of interpretations, that where the flow is coming from. So typically in this well, you can see these are the perforations, and there are some packers are put to isolate these zones, right? So we have multiple packers, open hole packers, downhole. We have a lot of perforations and different compartments. So the idea of production logging is to know the flow, or the zonal contribution from each compartment or each ICD. So you can see the final answer of the production logging is the flow profile, which is shown here on the down, and then a zonal contribution. So this track is showing basically the zonal contribution of each compartment or each ICD, right? Now, moving into the production interpretation in vertical wells, I'll show one or two slides for the vertical wells, because it's very simple, just to get an idea how it is different in the vertical well and how it is complex in the horizontal well. In vertical well, the production logging is simple. We use a spinner, like I said, which measures the downhole velocity in terms of RPS, or rotation, because the higher the flow, or higher the flow velocity downhole, the more rotations this spinner or the propeller will get, and then it reads different RPS, and it's normally the production logging data is required in multiple passes. So we do up passes and we do down passes. Up passes usually taken as a negative cable speed, and the down passes is normally taken as a positive cable speed. So why we do multiple pass? Because we get to have the spinner slope or threshold, right? So this is the cross plot of the spinner. So normally we select the zones, and from each zones we get the slopes and threshold, and these slopes and threshold are used for the downhole velocity computation. So remember, the spinner is actually measuring the rotation per second. So we need to convert this rotation per second into the velocity. And we use, is a very simple calculation. We use a slope and the cable speed and the threshold, right, in order to compute the downhole fluid velocity, because we do with the different cable speed. So each cable speeds having a different curves, because the faster you goes, the faster the spinner will turn, right? When you go up in the direction of flow, then if the both flow and the tool is going into the same direction, so that will reduce the spinner RPS. So we get a multiple RPS reading, even the flow is same. Even in the stable flow condition, let's say a well is producing or injecting 1000 barrel per day. Since we do a lot of down and up passes, that's why we get a different RPS because of the cable speed. When we plot this cable speed against the rotation, then we get a straight line, and from the slope of that line and the threshold, we compute the downhole velocity. So basic equation for the flow rate down to measure the downhole flow rate is very simple. Is we need a velocity, we need hold up, and we need the area. So what is the hold up? Hold up is basically fraction of pipe covered by each phase. When I say each phase, means it's in terms of producing well in the dual phase or three phase. Let's say oil water gas. So if a mixture is being produced, then we need to know what is the percentage of each fluid. But if it is an injector, like in this case, in this example, you see an injector, then we don't need hold up, because we know the well bore is 100% filled by either water or gas. Because if it is a water injector, then well bore will be filled with water. If it is a gas injector, then we don't need to know the hold up. We know the hold up is 1. The only thing we need to know is the area, which is provided by the caliper. So these production logging tools normally equipped with the caliper, which measure the downhole diameter, and then we use that caliper into the equations to know the flow rates. So it's a very simple approach, very simple interpretation in terms of vertical wells. We only need the velocity, hold up, and area. Even if it is injector, then we don't need hold up even. So this is for the vertical well. So how we use the hold up? Like I have this slide just to show what is an hold up. When I say hold up, because this hold up is used in this equation in order to compute the downhole flow rates. Hold up is defined as the volume of any phase, whether it's oil, gas, or water, as a percentage of the total volume at a particular point. So this is the hold up. Let's say a well bore is filled with different fluids. We have gas, bubbles, then we have water on the left side, and then the brown is representing oil here. So let's say a well bore is filled with a mixture of oil, water, and gas. So hold up is basically the percentage of each phase in the cross section of the pipe. Let's say in this scenario, the 80% of cross section is covered with oil, 15% with water, and 4% with the gas, but not to confuse with the water cut. Hold up is different than the water cut. Water cut, when we say water cut, is measured at the surface. If the well is producing 50% water, let's say, then the water cut is 50%. If the well is producing, let's say, 1000 barrel oil and 1000 barrel water, then we say the well is producing 50% water cut. But hold up is a fraction of the occupied volume inside the well bore, which is different from the water cut. So it is possible that you see a very little water, 15% water hold up, but at surface you are producing 40% or 50% of the water. So these are totally two different things, right? Just not to confuse with the water cut. Now, how we measure the water hold up from the probes? So we use electrical probes and optical probes that I showed in the DEFT and GHOST in the earlier slide, that these are a technology used for the direct measurements of the water holdup in a mixture or in a stratified, when the fluids are separated, or in the form of mixture. In both cases, we can use these electrical and optical probes in order to identify the water, differentiate or distinguish water from the hydrocarbon or gas from the liquid. So basically, the first probe we use is called the electrical probe. It works on the resistance of the fluid. We know the water is more conductive and the hydrocarbon is resistive to the current. So when the tip of the probe pass through the 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 hydrocarbon bubble, let's say oil or gas, then the circuit is break, and then it reads 0. It's mean the probe is inside the hydrocarbon, which is the non-conductive fluid. When the probe is inside the water, then it reads 1. So it's kind of binary measurements and it's basically counting the bubbles when the tool is going down or hitting the bubbles of water or mixture, in terms of mixture, or any type of mixtures downhole. So it can accurately identify the bubbles of hydrocarbon and inside the water phase, or the bubbles of water inside the hydrocarbon continuous phase. So this gives a direct hold up measurement, and its electrical probes can distinguish hydrocarbon, whether it could be oil or gas, from the water phase. Now, when we identify the water holdup, then the next thing is the optical probe in order to measure the downhole gas holdup. So the physics of the optical probes, as its name indicates, that it's used on the optical parameter of the fluid. The optical probes measures by sensing the change in the light in the gas compared to liquid. So there is something called refractive index. So when we see the refractive index of gas is different from the refractive index of water and oil. So we have enough contrast between the refractive index of gas and the liquid. So that's why this optical probe used the refractive index theory in order to identify the gas bubbles from the liquid. In the vertical well, the fluid is homogenized, or is flowing in form of mixture. So you cannot say that it's 100% water oil, but if the well is producing water and oil together, it will form a mixture, and this mixture will flow on the inside the well bore. And from the electrical and optical probe that I showed you in the previous slide, we would know the holdup of the phase, or the percentage of each phase, whether from the density measurement or from the probe measurement. The spinner, you see here, the spinner on the right hand side, this picture, the bottom spinner will measure the velocity of the mixture. It's not the velocity of only water, or not the velocity of only gas phase, but it's measure the velocity of mixture. And from the modeling, we can know the flow rate of each phase. It's water, oil, and gas. You see, this is the final answer product. Usually we give in the interpretation report that downhole, how the downhole flow profile looks like. So this is the example of the final answer product from the production logging for the vertical wells. Now, quickly talk about the horizontal production logging in horizontal well, which is the mainly the topic. That I just wanted to show you how two different approaches are used for the horizontal and vertical wells. So the production logging in horizontal well is having a totally different approach. Why? Because when the well deviation is more than 80 degree, like you see here, then when the production fluids, oil, water, or gas, flow inside the horizontal section of this pipe, then it behaves totally different than as if it's produced in the vertical pipe. So it's two different scenarios. Vertical pipe means is a mixture, but in horizontal, it's a totally different things. Why is totally different thing? Because of the gravity, we have a phase segregation. Why? What is mean by the phase segregation? We have three different densities of the fluid. We have a lighter fluid, which is gas, then a little bit heavier, which is oil, and the heaviest is the water. So because of the gravity, these three fluids will separate out in the horizontal section. But as soon as they reach in the deviated or the vertical section, they mix together. So when the well is drilled as a horizontal in the horizontal drain, and we want to know where the water or the oil or gas is coming from, we do the production logging. Then it's very important to know that how the flow is behaved inside the horizontal section. So the first thing is the segregation of the fluid will occur. So we will not have a mixture of the fluid, we will have a stratified flow. Secondly, we might have some stagnant water, which is again making hindrance or making problem for the production logging, because this water is stagnant there, it's not moving up or down, it stays into the, because of the trajectory, because you see the trajectory is forming a sump here. So the water might, because of the gravity, it stays there and it would not flow. It has no energy to flow into the surface, to the surface. Then we might have some fault, because of the fault, some gas breakthrough, so the gas can come. So there are some challenges in the horizontal logging. The one of the thing is the water recirculation. Like I showed, this water can be stagnant or making a recirculation. The oil which is on top of the water will push this water to flow. But this water, since it's heavy and has no energy, so it will go a little bit up and then falls back. So it's forming a kind of recirculation loop inside the valve bore. And it's very important to know how much the volume is occupied by this water, and what is the velocity of the oil, gas, and water inside the valve bore. So all these complex scenarios are not very easy to measure downhole, especially in the horizontal valve logging. We need advanced logging tools, advanced sensors, in order to identify the accurate fluid entry points in the horizontal valves. Now, you see here on the top picture here, fluid flow as a distinct stratified layer. So in the horizontal section, let's assume horizontal section, the water will stays on the bottom side of the valve bore, oil in the middle, and gas will always be flowing on the top side because it's the lightest phase, right? So because of the gravity segregation, the downhole flow, if it is the well is flowing or the producing three phases, or water, oil, and gas, they will be separated because of the gravity in downhole. So it's not any more mixture, it's a stratified flow. And if the well trajectory is perfectly 90-degree, when we say horizontal wells, it doesn't mean that it's perfectly 90-degree. So we know that when they drill the well, or the well placement engineers, they are drilling the wells, they are not always in 100% or in the exactly 90-degree. So we see areas with the less than 90-degree, we see areas with more than 90-degree. So usually well is not perfectly horizontal, but it is like a sinusoidal. Sometime it goes up, trajectory goes down, the change in the variation. So this change in the variation, even if it's a 1-degree change or 2-degree change, will change the downhole flow behavior completely. So let's assume a small portion of the horizontal section, like you see in this picture in the middle. On the right hand side, you see a lot of blue colors, means water, because the deviation here is 88-degree. It's not 90-degree, but it's just 2-degree below the perfectly horizontal section. So what's happening when only because of the 2-degree? Yes.
Said, sorry to interrupt you. Some people asking some question on chat, just to clarify.
Yeah, can we?
Will be at the end of presentation. Okay, so if anybody want to write any question, feel free. Yeah, we'll keep this part at the end of presentation for Q&A.
Okay,
Hello?
so
Okay, because some people writing question, just to clarify this one. We'll answer this one later. Okay, thank you.
okay. Okay, so let's continue. Yes, we can take the questions later on, right? So here we are discussing about the effect on the flow behavior in the basis of deviation change. So on the right hand side is, we call it upslope. All right. Why we upslope? Because the well is going onto the deeper direction. So on this 88-degree deviation, the water, since it's a heavier phase, it occupies more volume, but it moves slower. But on the top of that, the oil moves very fast, but it occupies a less volume or less holdup. Now, exactly on this 90-degree, in the middle, you can see when the gas is accumulated on this hump of this trajectory, because it's a lighter phase, because of the gravity, the water is in the bottom, then oil, and the gas is accumulated on this kind of, let's say, a small anticline in the well trajectory, right? And then when the deviation goes more than 90-degree, 92-degree, so it's more than 90, here is 90-degree, and here is less than 90-degree. So more than 90-degree, what's happening? Because of the gravity, the water flows very fast on the bottom, although it's in the bottom and it occupies a very small space inside the cross section of the pipe, but it flows very fast, and oil flows slower, but it occupies more volume. So you see, because of the small change in the deviation, how the downhole flow behavior is affecting the measurements. So it's mean when we want to know the flow, or we want to measure the downhole flow, the first thing we need to consider, what is the deviation at that spot or where we are measuring, to know the flow behavior. So if we are measuring here, then we need, and secondly, we need to know the localized velocity or localized holdup. So right. So because of this whole deviation, the flow regime or flow behavior in the downhole will totally change because of the small change in the deviation. And on the left hand side, you can see this picture of the flow behavior. When we have 88-degree, your velocity, gas velocity is high, but it occupies less volume, is like this. 92-degree, 90-degree. Measuring multi-phase flow has a long been challenge in deviated and horizontal wells. Why? Because of the change in the deviation. Now, here I hope you can see these small videos or movies of the flow loop, experiment done in the France in Schlumberger facility. So they created a loop for the flow to study or to research the flow behavior, how it's behaving. So the first one, they put a horizontal pipe, like a glass pipe, in 88-degree. They make it deviated like an 80, not perfectly horizontal, but they tilted to 88-degree, and then they inject from the side of the pipe, they inject two different densities fluid. One is lighter, one is heavier, and since it's transparent, so they inject kind of dye to differentiate from the colors. So when they do this loop test, you see how the liquid is behaving. So what's happening here? You see again, the red color is the lighter phase, which is very fast moving on the top side of the pipe, while the blue color, which is, let's suppose it's water, is occupying almost 80% of the well space. You see, it's a lot of blue colors. It's almost 80 to 90% occupying, but it's moving very slow. So this is what's happening when the flow loop is put on to 88-degree. Now, next, let's assume when the pipe is perfectly horizontal, exactly 90-degree, and we have a two phase, one is lighter, one is heavier, then how these two phase behaves. So you see here, they are equally distributed in the pipe, cross section of the pipe, and they are almost flowing with the same velocity, same speed, right? So this is what's happening in the when you have a totally perfectly 90-degree. Now, what happened if the pipe is, or the wellbore trajectory is more than 90-degree? So you are going basically down slopes. So when we do the flow test, so you see what's happening. The heavier phase is flowing very fast on the bottom side of the wellbore, while the light phase It occupies a lot of volume. You see a lot of red colors, which is the lighter phase, but it's flowing very slow. So this picture on the bottom, you see this is the velocity profile. Red color is the gas, which is on the top side. Although it occupies a lot of volume, but it moves with the slow speed, right? Similarly, on the 88° and 92°, you see three different scenarios and three different flow behaviors. So this is very important to know what is the deviation at that point where you are measuring the flow. And then from that, we need to measure the exact velocity of each phase and exact holdup of each phase. Now, to come up with all these complexities, which I have been showing in the previous slides, that how difficult is to know, to interpret or to get the production profile, production logging data in the horizontal wells, especially with the changing deviation, with the different types of completions and different scenarios, water sump. So all these challenges, we use an advanced array production logging tool, which use multiple sensors, right? Multiple sensors to measure the localized velocity of each phase and the localized holdup of each phase. So let's assume then, if in a stratified flow, when the gas is on the top and the oil in the middle and the water, let's assume when you have a single spinner, then this spinner is not giving you anything actually. It's half part of this spinner is inside water, which is flowing with a different velocity. Middle is in the oil, which is more representative of the oil because it's in the middle, but it is also touching the gas. So assume that this holdup or the distribution of gas, oil, and water inside the wellbore trajectory can be different. So single spinner is not working here or not measuring. Its measuring actually is affected by the velocity of different things. So it's not giving you a meaningful downhole measurements. However, in the array production logging tools or flow scan imager or FSI, we have tool design in a way that it has two retractable arm, and on the front arm we have 5 miniature spinners. Instead of one, we use 5 spinners. One is mounted on the housing of the tool on the bottom side, and then the 4 spinners are on the arm of the tool. So when the tool goes inside the well bore, it's open the arm like you see on the bottom picture. It's open up. Then on the front arm we have 4 mini spinner. One is in the bottom, and on the rear arm we have a sets of electrical and optical probes, like 6 of the electrical and optical probes, which is covering all the way from top to bottom of the wellbore cross section. So the top probes or top spinner will be inside the gas phase. You see here, you can see very clearly here. So when the stratified flow is going, this spinner on the top is reading the gas directly, the gas velocity or localized gas velocity. Then in the middle, these spinners are reading the oil velocity, and in the bottom, these bottom spinners are reading the water velocity. Similarly, the electrical and optical probes are mounted on the other arm on the same depth, and it's giving you the holdup of each phase, and they are clearly identifying the gas, oil, and the water phase. So this is the tool we use for the complex scenarios or complex, especially in the horizontal wells. Although this tool is very useful in the deviated well as well, but it's designed for mainly for the horizontal well logging, when the flow is very well segregated and not forming a mixture, and the oil, gas, and water are flowing at different velocities. So this tool will give you an answer of the production profile, and it can accurately measure the localized holdup and velocity. And from those localized holdup and velocity, we compute a complete 3-phase production profile in the horizontal section. And this is assuming also is there any recirculation or any complexity in the wellbore trajectory. Now, this slide is basically showing the location of the sensor in the vertical cross section of the pipe. So these dots, blue and red, they are the probes. Blue are the optical probes, red ones are the blue are the electrical probe, and red are the optical probes for the gas detection. And the black circle, they are the location of the mini spinners. So you can see we have 5 spinners and 6 sets of electrical and optical probes to have a full coverage of hold up and the velocity at a single depth. Usually, previously the horizontal wells were logged with the different sensors. And usually those sensors are very much apart from each other. So let's say one sensor is measuring the gas holdup, and which is on the top of the tool string, which is like 30 feet from the spinner, and the spinner is measuring the velocity. So it's very complicated when you are not on the exactly same point, the same measurement point. This tool is very short, and it has all the sensors in the in a very short length, and we are measuring the real-time downhole velocities and real-time downhole holdups from these sensors and the spinners. And here on the picture, you see some technical or the specification of the tool. This is in 111/16 diameter tool. Sorry. And the length is short, very short, is 16 feet. It has all these sensors, telemetry, and everything. Excuse me. These are the temperature and pressure rating, and then this tool is good up to the 958 pipe hole size from 2.875 to 958. So it covers almost all the pipe sizes, and it has a caliper. It can open, adjust itself with the pipe size in 4.5 inch, normally 6 inch, 7 inch. All these casing size up to 958. Minimum restriction is this. So these are some of the specification of the tool. And on the bottom, you again see a tool design. On the right hand arm, we have 4 spinners, one in the body of the tool, and each set of electrical and optical probes on the other arm, and one in the middle. Now, these slides will show a little bit about the FSI electrical probes. I already explained the principle of the electrical probes. It uses fluid electrical resistance measurements to identify the water in hydrocarbon or hydrocarbon in a continuous water phase. So it's work on simply basic binary principles. When the probe hits the oil bubble, then it reads non-conductive means 0 and conductive means 1, and it counts the bubble counts, and from those bubble counts from the algorithm, we can accurately measure the downhole holdup of water and hydrocarbon. On the other hand, optical probes, they are based on the fluid optical refractive index. So it has it sends a light source. It has a light source which emits in the small Y coupler, and when these lights sees in front of the probe, let's say if there is a gas bubble, so most of these lights which will reflect back, right? So if we have more light coming back, so it's identified that as a gas. If we don't have, if the light pass through the bubbles, then it's identified as a liquid bubble. So gas, or you see here on the graph on the left hand side, the refractive index of the gas is here, and the refractive index of water and oil is somewhere here. So we have a good contrast between the refractive index. That's how this tool is distinguishing between the gas and the water, or the gas and the hydrocarbon gas or the liquid. And it's working on the same principle. It has a probes. This is not this. I'm here in the picture is only showing one probe, but remember these are 6 probes located at the different locations inside the tool. So this is how we are measuring the holdup of each localized phase, oil, water, and gas, and the velocity. Now, this slide is showing the production logging, a typical production logging data acquired with the multi-array production logging tool. In this case is FSI. So let's see, this is the raw data on the left-hand side. What is this? On the leftmost side track is a gamma ray, which is an essential part of any logging. And in the production logging, it help us for the the depth correlations things. So we use this gamma ray. The depth tracked. The next to the depth track is the completion track or the valley sketch. The red ones are showing here in this particular data set. The red strips here showing the location of the ICDs, and black one are showing the location of packers. So we have multiple ICDs here, which are the inflow control flow devices. And then we have these devices or ICDs are isolated with the packers in the horizontal well. So this is run in the horizontal section, right? And these are the zones. Then we have these 5 spinners curves readings. So starting from left one, which is the spinner number 0, this spinner is mounted on the body of the tool, and this is the bottommost spinner. And on the rightmost side here, upper side of the pipe, this is the top spinner. So you can see the 5 spinners at different levels inside the valve bore, starting from spinner 0, 1, 2, 3, and 4. So each spinner is reading its own localized velocity and in the form of mixture. So when, let's say, the bottom 2 probes are inside the water phase and the top 3 probes are inside the oil phase. So the top 3 spinners are inside the oil phase. So these 3 spinners will be reading the oil velocity and the bottom 2 will be reading the water velocity. Are these 2 fluids, water and oil, they are flowing in the same velocities? Answer is no, or could be yes, depending on the deviation. So whatever is the downhole localized velocity of each phase, each spinner will, whatever the phase each spinner is into, it will measure the velocity of that phase directly, velocity, downhole velocities, right? And then this next track is the cable velocity. We usually do flowing survey or the shut-in survey at multiple cable speeds. So here also you see there are different passes of the spinners with the different cable speed. Now this image in the middle, green and blue, is showing the hold up image, downhole hold up image, and this is acquired from the electrical and optical probes. So on the left hand side is showing the bottom of the valve bore, and the right hand side is showing the top of the valve bore. So you see a clear fluid segregation. The water is residing on the bottom side, the oil is flowing on the top sides. So these probes will, from the software, we compute the holdup of each phase, means holdup of oil and water, and the velocity are provided by the spinner calibration of each spinner. And we know the phase velocity, and by multiplying the phase velocity with the phase holdup, and the area is provided by the caliper. By the way, this FSI is equipped also with the caliper sensors, which can measure the downhole diameter. So we have all these all the measurements into the one tool: velocity measurement, hold up, area. And then finally we process this data, we create the cross plots, we do the hold up profile, and then we do a computation in order to compute the flow rate downhole. And on the right hand side, this is the final product or the final answer of the production logging tool, running the production log tool. What we get finally, we get the production profile, and from the production profile we can know which ICD or which perforation is producing water or oil and how much is the percentage, which ICDs are inactive, which ICDs are producing highest amount of oil or water. On the top, let's say here, we see the water is coming from the top ICDs, so it's very easy to control the water from these top 3 ICDs. So this is the final answer, and here we have to decide what is the remedial work or the intervention we are planning for these wells based on the production profile. So it's not only the production data or production profile data. When you plan for intervention, you have to look at the other, you have to integrate the production logging data with the reservoir data, with the petrophysical data, logs, porosity, permeability. So it's not all in all that you rely everything on the production logging. Production logging gives you a valuable information of the production profile downhole, but nevertheless, this data need to be integrated with the other data sets to get a bigger picture on the reservoir level, a bigger picture on the well intervention level. So there's the thing. Now, on the right-hand side, you see the hold-up profile in the trajectory. This is the horizontal well, and then well is going on this is on the surface side. When it's turning, it's mean here on the surface, and then this is the horizontal section. So this slide was showing the typical flow scan imager raw data converted into the final answer product. What happens sometime? Because this tool, as I showed earlier, is mechanical. It has a mechanical spinners, right, and probes which have to pass through the bubbles of oil and water. It has a exposed tip of the tool which has to physically touch the water or oil phase in order to distinguish based on the resistance or the refractive index principle. So these sensors should always be touching physically the downhole fluid in order to measure. And this is why it's called the direct measurements without any assumptions, without any modeling. It's directly measuring the downhole representative velocities of each phase and and the holdup of each phase. But what happens sometimes? These tools come up in the because of the downhole condition with all these debris or sticky material, or sometime is like tar or some some emulsions or a lot of dirty downholes. What happens, these spinners, since these are very small and miniature spinners, they closed sometime because of the downhole condition. It's not always, but we see few times. Sometimes we see that these spinners are not turning very well because, or out of 5, let's say 1 spinner or 2 spinners are down, then we need to rely on the other spinners, since we have 4 spinners, and 2 phases. So sometime if 1 spinner is down, we can use the other spinner for the velocity computation. But sometime it happens that all these spinners are closed because of this is very rare, by the way, but it happens. The electrical probes are blinded because it's a small film of tar is stick to the probes and it makes it blind, so they cannot distinguish sometime water and oil or gas. So what is the what we have to do then? If the electrical probes or the spinners data is not working, then there should be an alternative. It's not the always, as I said, is maximum cases these sensors gives a good data, but in this condition we have to rely on the other measurements which sometimes are used in form of PNX tool or the nuclear measurements. We call it RST or PNX for the reservoir saturation tool. Those tools are used for the 3-phase holdup measurement because the probes are not working, and the water flow log is used for the water velocity. This is the spinnerless computation of the downhole direct velocity measurement based on the oxygen activation of the water. So it has detectors, 2 detectors, near and far detectors, and the neutrons bombards the oxygen, activates the oxygen in the flowing condition, and that when the oxygen or the water flows up, it measures the time, and we know the distance of each, because from the time and distance we measure the downhole velocity of the water, and this is based on the station log. It's not a continuous log, but we stop the tool and measure the water flow velocity at that depth, and then move up to next station and do this. Similarly, this is a continuous pass measurement for the three-phase holdup, and we get from these nuclear measurements the phase distribution in terms of holdup measurement, gas, oil, and water. Uh, Apart from the the prov measurement, so this is a totally different physics used for the hold-up measurements, three-phase hold-up measurement, whether it could be a vertical well, deviated well, or the horizontal well, and we get the water velocity from the other than from the other measurement other than the spinners. So sometimes we integrate this data into the in the model to compute the profile.
Okay, Mr. Sayed,
Yes.
do you expect you can close 10 minutes so we can start Q&A like at
Yeah,
at 8?
yeah.
At 8 in your
Yeah,
time? Okay,
yeah. Just
thank you so
not many
much.
slides remaining, so we
Okay,
have
thank
now.
you.
I have only 3 examples, which I hope I can finish in 10 minutes. So this is the first example. We logged with the flow scan imager, one of the well, where we see the early water breakthrough, or in what we call it water fingering. So in the reservoir, when you have a high permeability streak or the high layer which has a very high permeability, which is susceptible for the high water coming into the wellbore very quickly because of that high permeability, and sometimes the oil also flows to that zones, and then water follows the oil. So what happened in this particular case, when we log this well, what we found that 92% of the water was coming from the single point. Normally we see a homogeneous flow profile. A good profile looks like all the zones are producing, but sometime it happened that the all the production is coming from the single point. Like in this case, only 2 points, 92% from here, and the rest remaining production from this point. As you can see, also the temperature is giving a very good indication of the heating effect here, and sees a very strong entry of oil and water, and here also, right? So this, when we log the same well in the shut-in condition, same layers or the same points were making a cross flow. So we are getting some flow from the bottom point and then going into the top point. This is in the static condition when the well was shut in and nothing was producing at surface. And this is in the dynamic condition. So this was a very interesting scenario for the customer, for the client, when we run this log, and then they were surprised to see that their well is only producing most of the fluid from the two single sources. And we integrate this data from the image log to know is there any fracture or no, and we found out later on that there are some fault or fractures at these depths. So these are usual signature of the fault behavior or super K or the high permeability streak case, where when you see water and oil is coming from the uh, single point. Then what we need to do, we need to put a this is an open hole completion, so there was nothing, no perforation. The well was left open hole, barefoot. The next step, if we see this kind of behavior, then it's a good candidate for the inflow control devices, ICD completion, to put and to homogenize or distribute the overall flow in order to get the reservoir in homogeneous condition, not to flow from one layer, but we need flow from all the layers, or deplete from the all layers equally. Similar cases in well 2, we see all the water, although this was an oil well, but what we see is all the water was coming from the single source. The same thing and it could be either because of the fault or fracture in the zone. So these things happens, and this is the value of the production logging. When we run downhole, then we got to know that what is the problem inside the wellbore. Is there any early water breakthrough, early gas breakthrough? Why is water produced from single zone, or whether the water is coming from the only bottom or top? So to get a full picture of the flow downhole, this is the example number 2, and this is the showing also the value of FSI, or production logging tool, array production logging tool. You see on the rightmost track here, the wellbore is almost filled by 80 to 90% water, which is shown here with the blue color. On the top side, you see these red spots. These are the gas, the presence of gas inside the wellbore. Then you see a little bit of oil shown in the green color. All in all, you can see almost 80% of the wellbore is filled with water, but in fact, this well was not producing any water at surface. So it's quite surprising. When we go log downhole, this is all the water is stagnant water or a recirculating water, is not showing up to the surface. But the wellbore trajectory, was an horizontal open hole. You can see the completion here, well sketch. This was an open hole. So we go with the 5 spinner or the FSI tool. If assume it was a single spinner, then the spinner will be in the middle and it will be only measuring the water velocity, which is not flowing. So we got nothing. So thanks to the multi-array production logging tools, when we have a multi-sensor, so the top spinner in this case, for which was the spinner number 4, was able to measure the small portion of the oil and gas velocities, and while the bottom 3 spinners were in the water phase, which is not flowing. And you see these WFL water flow log stations were showing almost 0 velocity. So the water phase was not flowing. Only the top layer of the wellbore trajectory is showing the oil lighter phase and the gas flowing on the top side of the wellbore. And you know why this is keep changing when you have gas and no gas. Sometime we have, like in the top section, you have less water. This is definitely because of the effect of the well deviation. Like we said in details in earlier, that the small change in the well deviation can change the downhole holdups, downhole velocity. So it's very important to measure the downhole holdup and velocity at every level of these wellbore in order to compute the flow profile. So this is a typical of FSI data. You have 5 spinners, then you have holdups, temperature, pressure, and caliper data. So here the top spinner saved us by giving a good oil and gas flow profile downhole, and we get the answer or the flow profile from mainly from the top spinner interpretation, because that was top, and the second from the top, those were in the lighter phase, while the bottom 3 spinners were reading the water, were in the water. So those were not used in the interpretation. So this was the final production profile. You see the gas entry is the first gas entry is coming from here. By the way, this is a cumulative downhole flow profile, as many of you know already, that we show cumulative flow profile, which is like increasing rate. And here is the zonal, like each zone is producing. For example, this zone from 12,400 to 12,600 is only producing oil, which is shown here green. The next zone is producing little bit of gas and oil as well. So we give the percentage of each phase produced by each interval, if it is in the open hole, or each perforation, or each ICDs, or each perforated pipes, whatever the completion. So we give the zonal contribution of each section of the wellbore, and as well as the cumulative. Then we put the holdup profile, temperature, pressure. The interesting thing to notice here is a cool temperature is showing a cooling here, right? You see at this point at 12,200 we see a drop in the temperature. This is very well correlating with the gas entry, because gas normally cools down the temperature because it's lighter phase, and it has the temperature has a cooling effect. So we indicate this change in the temperature also indicates the gas. Although temperature curve can be used as a qualitative and as a secondary measurement, it has no big effect on the interpretation since we are directly measuring the downhole velocities and holdups, and we are converting those holdup velocities into the final flow rates. But the temperature always gives a valuable information of the inflow zones or the thief zones or the high permeability streaks, all these. So we have to look at the temperature as well, which gives a very good data. So you see what's happening here. The oil is flowing on the top side, the water is on the bottom. So this is the cross section of the wellbore. Now this is the last example. As I show that the FSI log is very effective in the horizontal log when the whole deviation is more than 80° or 85°. This is the common perception. But in the deviated well, for example, this well is 50° deviation, but still we need the FSI here. Why? Because this well a very low flow rate well, and it was only producing few hundred barrels of oil, only oil and gas. So the client, you see 450 and zero water at surface, and the well deviation was 50°. So when we go, the client decided to go with the flow scan imager with the 5 different spinners and compared the data with the conventional single spinner. So like you see here, 5 spinners, 3 of them are reading negative velocity. This is because of the recirculation. And the top 2 spinners, which is the spinner number 3 and 4, they are reading the positive velocity. So what is happening here? You see here these 2 pictures. Here on this side, on the bottom side, the water is recirculating, heavier phase is recirculating, and that's why some of the spinners are reading negative and some of the spinners, which is on the top side, reading positive. So 2 different direction of the flow happening here. So that's the value of FSI. Even in the deviated well, it's accurately identify the low flow rates up to 4. You see, we computed 490 barrel of the oil. But if the same well afterward was logged with the single spinner or the conventional tool, which has only 1 spinner and which is only in the middle of the well bore, so that spinner was not able to quantify it. It gives the profile, but it was only computing 200, underestimating the oil. Why underestimating? Because that spinner, single spinner, is not measuring the representative velocity. Sometimes is affected by the recirculation, as we see in the flow scan, that 3 spinners were reading negative velocity, 2 spinners were positive. But since it's a single spinner, it is affected by everything downhole WhatsApp. So it's confused. The spinner is confused here whether to read the positive or negative velocity. So it's underestimating and it's not giving the representative velocity. This is the velocity computed from the single spinner, and this is the flow profile computed from the single spinner, but it's only computing 200 barrels. So that shows when we compared both data with the conventional spinner and the FSI spinner, it shows the value of the production logging multi-array tool. Even in the highly deviated, not highly deviated, but let's say 45 to 50° deviated well, we still can see a water recirculation. We still can see a different phase segregation. So we need localized hold-up measurement, localized velocity measurements in the deviated well and also in the horizontal well. So that brings to the end of this presentation. If you have, I know you have many questions, so please feel free to ask the question. Thank you very much.
Thank you, Mr. Sayed. It was really informative lecture. And this subject that you present, even for Iraqi market, okay, locally, is really important because we have most of our field is going for deviated well, okay, and the problem you present, merely the last example, I can say we encounter on daily basis, okay. So thank you so much. There is few question on the chat box. You can't see the chat box.
Let me check. Yeah. Yeah. Okay. So
I believe first question come from Muhammad Saada. Okay, he
Masada,
asking, yeah,
how PL in horizontal well handle high water cut environments, sort of detect thick oil drops, high viscous emulsified in water. So
I believe he's talking about emulsion, and this subject
emulsion,
is
yeah,
really,
emulsifying.
I believe
Yes,
this is
yes.
really a complex subject. You know, it's not easy to
Yeah,
detect.
when we talk about the it's not happening all the time, but yes, it does happen in some of the wells because it's specific conditions when the emulsion is happen downhole, provided that the velocity should be very high and the well should be, very well mixed. So we know that there are some cases where the emulsified or the high viscous oil form emulsion in, and it's doesn't allow probes to work properly, because those probes work on the principles of the bubble detection. When those oil bubbles in water or water bubbles in oil, they are covered with a thin film of oil, then the electrical probes will not be able to see that. So what is the second approach? If we see emulsified, then, and we are the probes are underestimating the water, or we are not able to measure the holdup, then we use the nuclear measurements. Like I showed, the water flow log or the three-phase holdup, nuclear measurements gives an alternative three-phase holdup regardless of the emulsion, regardless of the any flow condition. It gives a independent measurement, independent from the probe or the mechanical measurements. So we can still solve the case in the emulsified fluid from the three-phase nuclear measurements and the water measurements. So that's the approach we usually do.
Okay, second question from also Muhammad Mahmoud, I believe. Are these electrical and optical probes? I believe the data come from uh, come from waveform array.
Yes, yeah. So basically, yeah, there is a waveform for each electrical and optical probes. Each probe is measuring the waveform, and that waveform is processed downhole inside the tool, and it gives by setting some fixed thresholds and this, and it gives the final the holdup. So yes, it records the full waveform. From each point, each sampling, and that translated into the holdup.
Okay, thank you. Another question from Mr. Amal Aliyev. He's asking about the importance of spinner calibration. Okay, I believe it's really
Ye-
critical subject.
Oh
Okay.
yes, yeah. Okay, let me go back. Yes, spinner.
Mm,
Why what is the importance of? So let's assume, like in vertical well, like this slide, we have spinner data here. So uh, we have to make a cross plot based on the cable speed on the x-axis and rotation per second or RPS on the y-axis, to make with the different cable velocities to put on in the same cross plot. So why we do that? What is the importance of making this cross plot? Or the basically that every tool has a different design, and every tool behaves differently in downhole condition. When whether it is inside the oil phase, the spinner might behaves differently than it is in the water phase, because of the density, because of the many things, and the design itself, because each spinner has the magnet inside, so which is converting the rotation into the electrical currents, and those are there are bearings inside. So those design, the mechanical design of each spinner has a different rotation per second and the different fluids. So the importance of the spinner calibration is to to eliminate the design of the spinner and the its behavior in different fluids. So that's why we make a measurement in different cable velocity and put in a single plot. And when we put all these in single plot, that should follow, each zone should follow a straight line. And when this line is intersecting at an x-axis, that's the actual downhole velocity. Because we are going up and down with different passes, so we don't know what is the exact velocity, because the velocity of the RPS of the spinner is affected by the tool movement. So we need to eliminate that tool movement, we need to eliminate the slopes and different things. So we put all these in cross plot in order to accurately measure the downhole velocity. So that's the main purpose of the spinner calibration, and it's very important, by the way.
Okay, so I don't believe we'll have time to take all these questions. Okay, there is another question from Mr. Abbas Muhi, student from University of Baghdad. He's asking about depth of investigation. There is no depth of investigation for BLT. It's reading
Yeah, it's
instantaneously,
reading. We are inside the
directly.
well.
Yeah, well bore. Only the temperature you can see. Okay, behind the casing, unless if you're on noise log, which is different story we discussed last year. I believe Mr. Abbas, you can talk if you like. You can open the mic.
Good evening, Mr. Mazen, and
Hi, how
thank
are you,
you
Mr.
for
Abbas?
Mr. Said. Welcome.
Most welcome.
Thank you,
Most
Mr.
welcome.
Mazen, and thank you for Mr. Syed Aamir for this presentation. To save the time, I have two questions about the advanced log for horizontal well. As you know, in Iraq, almost our well is horizontal well. I see small difference between FSI and MAPS. FSI, if you have just 5 spinner. MAPS, you have 6 spinner, and also the shape is different, right? This is the
Right.
first question. Right. Second, what about the cable speed in horizontal well? For vertical is easy. You can use 4 speed, 10, 20, 30, 40, and do what you say about the calibration for a spinner. What about horizontal well? Do the same, because we
Okay.
done because we done the BLT either, for example, by tractor or coil tubing. For 600
Right.
meter, very difficult to do speed and do cable speed for time up and down. Third,
Okay.
what about the noise log during the BLT? Because BLT in horizontal give me just one way, not confirm exactly where is the water coming from, where, or contribution for a fluid. Maybe noise you can help us. Thank you. This is
Yes.
my question.
Okay, thank you. 3 questions. So taking one by one, the first question you asked was about the comparison of the flow scan imager or FSI with the other tools available in the market. They call it maps. Those tools also have a 6 spinner. Is like I would say like nowadays, a race for the mobile camera. You put 6 camera. Some people put 8 camera, but it doesn't means sometime a lot. Putting more sensors doesn't mean you are get. Anyway, nevertheless, each tool has its own design, but we still think that this design of the FSI, because this is based on the 2 arm, right, and the one arm facing the front side is having the spinners and the back side having the hold up measurements, while the maps has a circular design. So that tool spinners will always be rotating. It's not keeping on the same position, though each spinner is sometime the same spinner, sometime is in water, sometime in the oil, sometime in the gas. And because of the tool rotation, it has high chances of clogging downhole, or the sometimes spinner stops. So each spinner, and they are also measuring the phase velocity from those spinners. But yes, it depends on the what is the objective of the job and how accurately. But it's a two, I would say it's a 2 different designs, and both works. We both measure the downhole velocity, whether it's in you put the sensors in the vertical cross section or in the circular arrangements, whatever. So it's measuring the same thing. Now, the second question was about in horizontal logging, how we cope with the different cable speeds. Sometimes the horizontal wells are very long, by the way, and it takes hours and hours to do a single pass from top to bottom, especially when you are doing with the tractor with the slow speeds. So usually we have to rely on a single pass. So in production logging tool, because since it's using the multi-array sensors measurement, direct measurement downhole, if everything is working fine, then one pass is enough. We don't need multiple passes. However, for the spinner calibration purpose, when we are in the deviated section or the vertical section of the pipe, let's assume like 200 feet, we take the section of 200 feet and we do multiple passes there. Very short, because that doesn't take much. Maybe in half hour you can finish all the passes. Those passes actually we use as a calibration passes to obtain the spinner threshold and slope, and that slope and threshold applied on the main pass which is logged in the horizontal section in order to compute the downhole flow. So it's okay even if you have a single pass, and if everything is working, it's enough. We do processing or interpretation on many wells where we don't have luxury of having multiple passes. So we have sometime one or two passes, and then we can give a full detailed production profile based on passes. The third question was about the noise. Yes, noise is a very good measurement. It can also see behind the pipe as well, but that is qualitative. You cannot quantify the flow rates from the noise. Is very hard from the temperature because you need modeling. Here with these sensors, you are directly measuring the downhole velocities and the hold up, so you can easily convert downhole rates, or you can identify the downhole fluids. But the noise is basically used in the mainly in the leak detection. And when you have a complex horizontal well three-phase flow, noise sometimes it's very hard to interpret the noise data, because we hear noise but we don't know where it's coming from. It's because of the gas entry, because of the deviation change can change the noise. We see the deviation has a lot of big impact on the flow. So could it be deviation and we have a noise signature and we are misinterpreting as a flow? So it happens that the noise is very qualitative and it work very well in the vertical valves for the leak detection cases, but not in the complex horizontal valve three-phase scenarios.
Thank you. Thank you, Mr. Sayed. Okay. And thank for our attendees for their question. And we are sorry if we have some time limit to answer all these questions. Okay. Mr. Sayed will have another lectures. Okay. And I'm not sure, like in the next couple of months with us to show us a case study for interpreting production log data using TechLog software. I'd like to thank our attendees. I'd like to support of Schlumberger and Mr. Sayed to take this time for knowledge sharing. Okay. Dr. Mohammed, do you want to see anything before we conclude?
Yes, Mr. Mazen. Thank you for Mr. Sayed about his lecture. Thank you for Schlumberger Company and for all attendees. We will meet you in another lecture soon, and SPWLA welcome to you in Iraq at any time. Thank you.
Thank you all, and
thank you very much. Thank you for attending.
Thank you, and see you next month. Bye bye.
Thank you.